So you've got your world's main mechanics working, but whenever your characters level up, you want to make sure that the next time they enter your world, their progress is saved. That's where data storage comes in, and today we'll walk through everything data storage related and how MapleStory Worlds makes it easy to implement a persistent save system for your world. Let's begin with a brief overview of data storage systems and the different ways to save your data. Data storage has 4 main types of spaces, each with a different purpose. We have global, user, creator, and sortable. Each one differs in its scope, access method, and type of data. Global data storage, for example, allows you to store data based on a per world basis, meaning that the data you save here is unique to the world itself, and each subsequent world you create will have its own version of data. Global data storage can also hold multiple containers, so to speak, of data. Imagine a global data storage as a globally accessible data warehouse that houses several containers of data and can be accessed by all users connected to the same world. Data contained within global data storage must be in string format, so this means that any complex data types must be serialized to string format using things like our HTTP JSON encode or util-logics table to string to serialize tables to strings. User data storage, on the other hand, is intended as a storage space assigned to each individual user and must be accessed by the user's ID. So this means that you need to know the user ID to access this data storage space, and the space houses a single container of data that this player owns. Similar to global data storage, only string values can be stored here, and complex data types must be serialized to string first before saving. Creator data storage is a storage space tied to the creator across all worlds that the creator owns. This means that you can save data from one world that can be accessed by another. Like user data storage, creator data storage can only house a single container of data. And like the other two we've discussed, you must utilize string values when saving data to this data storage. The final type of data storage is sortable data storage. Sortable data storage is very similar in structure to global data storage in that it can house multiple containers of data. However, sortable data storage is special because it's intended specifically for handling numerical values. As the name implies, numerical values stored in the sortable table contains methods to allow for sorting of values stored in the data table, as well as other useful functions like incrementing or decrementing values. Each of the data storage types we've discussed are retrieved through the data storage service. And as you can see, each retrieval function requires a different set of parameters to access which container of data we'd like to retrieve. Global and sortable data storages, for example, can hold multiple containers of data and thus requires us to specify the name of the said container. User data storage houses a single container per user, so we need to specify the user ID when retrieving this data. Creator data storage can only house a single container of data, so we don't need to specify any special parameters during retrieval. So here are those functions again to retrieve the data storages. And as mentioned, each of these require different parameters when retrieving due to their different natures and use cases. On the right side here, we can see 2 different versions of the delete functions. One with AND_WAIT and another with async. The AND_WAIT suffix means that this method is a synchronous function, meaning that until this function is fully executed, in the case of the delete function, until all data is fully deleted, the code execution will be fully halted. The async method, however, will allow the method to run in the background while the code execution continues. Instead, we pass in what's known as a callback function, which essentially is a function that we pass in as a parameter to say, once you finish execution, call this method. We'll be able to see how async definitions work shortly. Once you've selected and retrieved the data storage type you'd like, you'll now want to be able to work with your data. There are 3 main types of interactions for data storage types: get for retrieving data, set for saving data, and delete for deleting data. We can see the 3 ways to interact with data using the global data storage as an example. Many of the examples we'll see are utilizing the global data storage type, but the methodologies here will be the same across all different data types. First, set and wait allows us to assign a string of data to a target key. As we saw previously, we can see the global data storage retrieval method through the data storage service and using the get global data storage function. Remember that the global data storage allows for multiple data containers, so the storage name here is the name of the data storage we'd like to retrieve. If the data container does not yet exist, it will create a new one, so it's important to keep the spelling correct here and retrieve the correct data storage space. We can then call the set and wait method by passing in the key that we'd like to assign our data, along with the data that we'd like to store there. The error code, as we'll discuss shortly, will let us know if the operation was successful or if the operation failed. Now that we've saved the string of data to a key, we can use the get and wait function to retrieve the data from our global data storage. And this takes in the stored key that we used as an example. And before we can retrieve any data here, the key must of course already exist. We've already done so of course this key will exist. We'll again get the global data storage from the data storage service and use the get and wait method to retrieve our data. This time we return two values. Error code for the error that was returned. If it exists, it will be 0 if successful, and 1 for the value that we just retrieved. Finally, the delete and wait method allows us to delete a data entry stored to a key. We'll once again retrieve the global data storage from data storage service, and we'll pass in the storage name to retrieve the correct data space. With the last few examples, we've been using the synchronous versions of our methods, but as I mentioned previously, there are asynchronous versions of the methods as well. Here we have side-by-side synchronous versus asynchronous versions of our get, set, and delete functions. And as a quick refresher, the synchronous functions have the and wait suffix and halt code until the operation is fully complete. The asynchronous function, on the other hand, have the async suffix and have a parameter for a callback function that we call once the operation is complete. On the left side synchronous function, we can see that we simply pass in the key and it returns the error code along with the return value. On the right side asynchronous function, we can see the key as we did for the synchronized function, but we can also see a function definition passed in as a callback to be called once the method is finished executing. As we've seen through the function definitions, most of the methods in the data storage service return an error code, which tells us whether the operation was successful, and in the case of a failure, provides us a hint of what the issue could be. Here we can see the possible error codes that can be returned from our various functions. 0 means the operation was successful, and any other error code lets us know that the operation failed, along with the reason to help us debug the issue. When using our data storages, it's recommended to have handlers built into your code to at the very least output the error code, so when something goes wrong, you know why. When retrieving data, there may be cases where a lot of data is retrieved at once. To manage request limits, certain functions may return data as pages of data. Imagine a small booklet of data where each page contains a small chunk of data and you need to flip through each page to see the rest. On the left side, there are some of the methods that may return data as pages. In the case that they do, we'll have to iterate through each page and load in the next page as we traverse through our theoretical booklet. In the example on the right, we can utilize the get global data storage pages async function to return a list of all the global data storage pages that we have stored. Because it's an async function, we pass in this function to handle the result after it's completed. We get as a parameter to the function the error code along with the pages. If the error code is 0, we'll proceed to iterate through our pages. Our pages variable will initially have the very first page of our data. So our pages variable will initially have the very first page loaded, so we will have to call the getCurrentPageDatas to retrieve the data. We can loop through each of the data storages and call delete global data storage and wait to pass in the name of the data storage to delete that table. When we call move to next page and wait here to flip to the next page, we'll repeat this process over and over until the last page flag is true, in which case it'll tell us when we've reached the final page. More often than not, it's ideal to group your get, set, and delete requests together to save on the number of requests made and ultimately keep your requests under the limit, as we'll discuss later, through a methodology known as batching. Batching allows us to group requests in a single call to optimize our total number of requests for our data. On the left, we can see the various batch functions associated with getting and deleting, as well as their async and synchronous counterparts. On the right side, we can see an example of a few batch requests. In our first example, we're initializing our keys table to contain dummy data named keys1 and keys2, and we can request both of this data together as a single batch get request, which returns us the pages for our data. Then with the pages we receive, we can utilize the same structure we saw before to loop through our pages and read the data. Next up, we have the batch sync delete with the same two keys of data. We'll simply pass in the keys table to delete all the data contained within our table. Finally, in our last example, we have our key value pair with key name key1, key2, and key3, along with their corresponding values, value 1, value 2, and value 3. And we'll pass this table of data into our batch set and wait sync request and set our data based on the table. For all three of these methods, it's possible that some requests may succeed and some may fail. So in the item page's return value, deleted keys return value, as well as the success keys return values of all three of our batch examples, it will return a list of keys that were successful. The atomic set and delete is an all or nothing batch request method. This means that either all items are returned successfully or none are. This contrasts with the earlier batch method examples where it was possible to return a partial success. These atomic methods are prefixed with transact. In our example to the right, we can see two tables of data, T1 and T2. T1 is passed into sync batch set request and T2 is passed into an async batch set request. In either case, if any of the keys are not set successfully, the entire operation will be considered a fail. We've got another example here, this time with the transact delete. We again have two tables of keys. Keys 1 is passed into a sync transact delete, and keys 2 is passed into an async transact delete function. In either case, either the entire operation is a success or none of them are. As we work with our data and multiple clients start to save to our data storage simultaneously, we may need to make sure we're versioning our data properly. This is where KeyInfo Data may come in handy. There are three parts to KeyInfo Data. Of course, we have the key, as we've seen up until now, but we also have the tag and version. The tag will allow us to group our data together, so if we wanted to, say, retrieve a list of all data storage values that have the inventory tag associated with them, we can do that. The version will allow us to store a value for the version of the data, which we can use to compare two possibly conflicting values of data and make sure we accept the proper version. You can identify methods that have key info associated with them by looking for the by info keyword in their function names. In our example on the right, we have examples of defining key values for a particular key. In our first example, we're doing a single sync set request of key data, and we can see two different ways of assigning key info here. The first is by passing the key, tag, and version into the constructor for the data storage key info type. In the second, we can simply create an empty key info and selectively define our key info data and choose to omit fields that we don't need. Our second example does the same thing, except by using the batch sync get request. So now that we've assigned key info to our data, how do we manage versioning? So in this example, we are retrieving our data storage that we assigned global DS. We'll then create a data storage key info definition here, and we'll assign key as our key value and version 1 as our version value. We'll first set our data by passing in our key info by passing in the key info that we created along with our initial value. Then we'll modify our key information to be version 2, and we'll again set our data based on our new version 2 with our new value 2, to our new version info. Then finally, we'll set our key info back to our first version and attempt a get request on version 1. Here, we're still able to get version 1, meaning that both versions exist in our data assigned to the same key, just with different version values. In this next example, we'll do something very similar, except this time by using the data storage key info constructor. We'll assign our initial version as we did in our previous example, then we'll assign our new version with the value new value to the same key. Finally, we'll set the new key info to the old value, which will effectively overwrite our new key info to our old value, rolling back the changes we made to version 2. If desired, we can also retrieve a list of all the versions that we've assigned to our data and even filter by specific dates that the version was created. In this way, we can compare and utilize the create time and the version info to double check which data is the most recent and roll back versions as necessary. With all of the data methods we've seen so far, we do have usage limits that we must adhere to and optimize around as we design our data storage structures. Limits are assigned not by the data storage type, meaning global, user, creator, or sortable data storage types, but instead are calculated based on the function group that is associated with. This means that all storage types, global, user, creator, and sortable, share the same limits, but are separated not by the storage type, but by the function group that is getting called. Please reference our Creator Center guides for a more detailed list on the methods associated to each function group. Each function group is periodically assigned a number of credits paid per minute. This limit is capped at twice the number of credits paid per minute. At any given time, you will never have more than twice this number paid per minute. The number of credits paid per minute also scales based on the number of connections you have to your world. So the more users are connected to your world, the more credits are paid. Different function groups are assigned different number of credits paid per minute, and each call to a function costs a single credit. Notice, however, though, the get, delete, and set methods have slightly different credit consumption rules. The consumption of credits for these three groups, get, set, and delete, are measured not so much by the number of requests, but more so based on the size of data. Per every 4,000 bytes, a single credit is consumed, but never less than 1 credit. So even if you were to save less than 4,000 bytes, you will always use at least 1 credit, which is why batch requests can come in very handy. Rather than requesting multiple times for individual pieces of small data, you can instead batch multiple calls together to consume less credits overall. We can see here an example of how credits might scale based on the number of users. Here we can see what the numbers might be for a single user. For list data storage, we can make up to 12 requests per minute with a maximum of 24 requests per 2 minutes. For delete, we can see a 2-minute max of 104, which amounts to roughly 416 kilobytes, and the get and set with a 2-minute max of 220 credits, which is roughly around 880 kilobytes. For 10 users, our list data storage scales up to a 2-minute max of 60. Our delete scales up to a 2-minute max of 140, which is about 560 kilobytes, and our get and set scales up to 400, which is roughly 1.6 megabytes. And finally, with 100 users, we can see a 2-minute max for the list data storage, 420 requests, and our delete with a 2-minute max of roughly 500, which is about 2 megabytes, and our get and sets with a 2-minute max of 2,200, which is roughly 8.8 megabytes. So as you can see, the numbers will continue to scale the more users you have concurrently connected to your world. And that's it for today. Thank you so much for joining me in today's session as we go over the ins and outs of data storage API documentation. Hopefully by now you have a stronger understanding of our data storage API to begin saving data in your own worlds. Happy creating!